All right. So kind of get going here. So that fifth problem set, and where's it at? Oh, right here. I had kind of set to be due at the end of the day today. If you want a little extra time, I'm going to update this. If you want to stop by office hours for last minute questions, I'll kind of change this to be at the end of the day tomorrow. So if you have anything you're kind of still working on, want to make some kind of last minute changes, I'll change this due date to be the end of the day tomorrow. If you want to stop by office hours in the morning, 9:30 to 12:30, last minute questions, that'll be an opportunity to do that. Okay. That quiz I still have set to be due at the end of the day on Thursday. So if you're looking at those practice problems, we've really worked through, I think, every single thing on there. We will revisit a little bit. So if you come all the way down here, it's mostly interaction terms. We talked a little bit about kind of bias that can exist, selection bias, measurement error. We'll look at a little bit more measurement error topics today, just kind of rounding out that discussion we had last week. We'll then jump into panel data, right? Also, just wanted to mention kind of that practice exam that's up there. I will get a second one added in. I'm trying to kind of make sure that's going to be the most effective use of your time. So trying to make sure that practice exam has questions that look pretty similar to your final exam as I'm writing that. So you'll see a second practice final kind of pop up here. If not tomorrow, kind of depending on how busy my office hours are, for sure by the end of the week on the end of the day on Friday, I'll have that kind of posted. So we've got this week, we'll look at panel data primarily. Next week, we're going to look at something called instrumental variables. And then it's basically, we're in that week before finals. Right? So we're getting close to the end there. There will be one more quiz and one more problem set. So I'll get those posted up at the beginning of next week, and it'll be kind of due at the end of the day, Friday, that week before finals. Okay. So just kind of a roadmap where we're going. Before we kind of dive into things, I don't think I have anything housekeeping stuff. Any questions from me before we jump into material here? Okay. So I'm getting a little bit nervous as we get towards the end, some of the attendance here. I can't reiterate enough kind of making sure you're keeping up with things. You've got a lot of tools, generative AI when it comes to these problem sets and these quizzes, you're not going to have that in the final, and it carries a pretty good weight. Okay. So we'll kind of start thinking about where we left off with data issues. We kind of talked through these like selection bias, not response bias. We thought about random missing data, data that was correlated with X, and kind of where we left off. And I think I introduced this idea with selection bias, but our missing values or our measurement error can also be within not our X variable, but our Y variable as well. So we'll kind of look at some of this, primarily kind of looking at this in Stata, but I'll kind of try to give you a little bit of information kind of here along the way. So if I'm thinking about, or pull open that Monte Carlo simulation view file that I have posted under last week's files. So if you come up here, we're looking at this guy right here. Right? So let's assume, so we're going to scroll down here. Actually, let me make sure I'm getting my file path set here. Can't do it from my device because my iDrive is different. So let's say I open this up. If I don't break the computer here, there we go. So I'll make sure. Hold on. Oh, it's a bigger file than I thought. So we're kind of waiting here. So while we're waiting, there we go. So we kind of think about if I've got a regression equation that looks something like this, right? If I just have completely random measurement error in my Y variable, it's almost like the Y value I'm observing is the actual Y plus some additional error term. Okay? So when I run my regression, I'm not using the actual Y values. I'm using kind of those observed Y values that have this additional measurement error in them. So all that really does is create this error term, right? Call this, I don't know, E2, however I wanted to kind of denote this, where if it's completely random, the expected value of this new error term, which includes the original error plus the measurement error, given my x values, should still be equal to 0. Okay? So it shouldn't really matter. That was kind of our assumption that we needed to be met for our regression results to be unbiased. So I'm going to go here and paste this before we go back to, there we go. And this would be well, 12 terms. Okay. So if I have measurement error that's completely random, then I'm okay. All right. In fact, my estimate for beta 1 should be unbiased and it should be consistent. I shouldn't have any difference in our statistical significance. If this component of the error, right, the measurement error starts to get correlated with our x or our y values, well, then this will no longer be the case, and we're going to have some bias in our estimates. Okay? So I think this is probably easier to think about, kind of proving this to ourselves with data. But the end result is, if you have measurement error in y, if it's completely random, uncorrelated with the actual y values, which y would be correlated with x, so if it's correlated with y, it has to be correlated with x, right? If it's completely random, then that expected value of our error term will still be equal to 0. If it's not random, well, then that expected value of our error term, which technically now includes the original error plus our measurement error, for different x values will not be equal to 0. Right? So what we're going to start looking at here is, so I'll get my global path set correct, and we'll kind of come down here where we left off. So I've got here, oh, I scrolled too far, measurement error in my dependent variable. Okay. So I'm going to run this line of code here, where all I'm doing is I'm opening up that life expectancy data. I'm kind of scaling GDP just to make the coefficient easier for us to look at. And then I'm creating this random measurement error that's just somewhere between 0 and 300. It's completely random. And then it's getting added in to that y variable of GDP. Okay. So the actual regression I'm now running is GDP with the measurement error, and then kind of trying to predict it with BMI. So this is my y and my x variable. My y variable is now kind of that y tilde, or it contains this measurement error. So I'm going to do this now 1,000, because that's what we did last time and it took too long. So I'm going to do this 100 different times. I'm going to store the coefficient and the standard errors, and then we're going to take a look at what that looks like. All right, because if I just do this once, you know, it could be completely random. I could see a higher or lower estimate, but if we do this enough times, on average, we should still see that same coefficient estimate. So I'm going to come here. I'm going to create this program. It's going to include this measurement error, do that 100 different times. I'm then going to summarize that coefficient that I'm seeing. Okay, so I'm going to go ahead and do that. Takes a little bit of time to run. So we get this estimate of 60,088. Okay? Now, if I didn't run this kind of simulation where I had this different measurement error created, if we went back to our kind of original regression where I didn't have measurement error, what I'll end up seeing is, sure enough, without measurement error, I was getting that same coefficient as I was with that random measurement error. Okay? So my coefficient hasn't changed at all. Okay? Now, what should also be true is from my original regression, so this is just the actual data, it doesn't have the measurement error built in. My standard error was what, 11,700-ish, right? So if I come back down here and I run that same file where I have that random measurement error, but now instead this time, instead of looking at that coefficient, I'm going to actually look at that standard error. So if it's completely random, not only will my coefficient not be impacted, my statistical significance shouldn't be. So I'm going to go ahead and run this, and sure enough, my standard error across these kind of random 100 random different measurement error samples is exactly what it was before. So good news for us, if the measurement error in my dependent y variable is random, we don't really have to worry about it. It doesn't change our estimates. Okay? Now, that won't be the case if I come down here to the second scenario, where I'm going to do a very similar thing. So once again, I'm just going to run this so we have it to compare to. This is the actual y values of GDP. So I'm going to go ahead just so we have this as kind of a comparison, that was our coefficient. If I do this kind of thought experiment, where I do this 100 different times, I generate some measurement error, but now it's random. But notice it's a random number that gets multiplied by. In fact, actually, what do I want here? Let's say, oops. It's kind of not random, right? It depends on kind of these X values, or I could kind of have it depend on these Y values. So the measurement error in my Y variable is not completely random. It depends on this X variable I was using to try to predict Y, which is BMI. Okay. If that's the case, now when I run this regression 100 different times and then summarize those coefficients, I don't find 60,088. I get 60,600. Now, it doesn't seem like it's off by much, 600 too high, but we're doing large values here. I mean, depending on the sample we have, we don't know how large that bias is going to be here. It's a positive bias. We're seeing estimates that are too high, and that's because that measurement error was positively correlated with that X value. I mean, we forced it to be. And in practice, we don't know what this measurement error's relationship is with these X variables. Okay. So if we have non-random measurement error, our coefficient estimate will change. Now, just to show you why this matters, if I don't know what the measurement error's relationship is with X, maybe it causes my estimate to be too high. But down here, I had the exact same kind of setup, but now I'm looking at random measurement error. And notice I put a negative sign up front here. So I'm making that correlation of my measurement error with X not positive, but negative. So what this is going to do, I'm going to take a wild guess, if the positive covariance between X and this measurement error cause our estimates to be too high, if there's a negative relationship, that's going to cause our estimates to be too low. Okay. So as far as I would probably ask you a question like this on a quiz or the exam, I won't ask you to put a directional sign to this bias. All you need to know is that if you have non-classical measurement error in that dependent variable, so it's not random, it'll cause your estimates to be wrong. If it is completely random in that dependent variable, doesn't matter. So I'll go ahead and run this regression where I now have this negative correlation between the measurement error and Y. Now, when I look at my average estimate across these 100 different samples, now I see an estimate that's actually a little bit too low. Now, the size of this bias, right, depends on how random that measurement error is, okay? Now you can, so like, let's say I do something crazy here, like, I don't know, add a couple zeros in. Not only is this going to estimate be too low, so instead of 60,088, it's now what, 59,500. That bias, the larger that measurement error is, the larger that error we're going to be making in our coefficient estimate. So if I go ahead and do this exact same thing, but I now have this much larger random measurement error, we're waiting. Whoa, now it's driven all the way down to 9,000. Okay? So we're concerned with measurement error if it is not classical, it is correlated with X, and we're concerned about it if we think it might be really large. So an example of this might be, if I'm looking at self-reported data and I ask you what your income is, you're off by 1,000, that's a really small percent of actual your income. Well, there I might not be as concerned with my measurement error. I know it's going to influence my coefficient, but maybe not by a whole lot, right? Now, where might I have to be concerned? If I had my, let's say I was trying to predict the number of hours studied based off of students' alcohol use, right? And I know that maybe the number, I don't know, actually we'll flip it. Let's say I want to estimate their alcohol use based off of their hours studied. And I think, okay, this measurement error that exists in alcohol use, they're likely going to lie to me a lot if they're using it way too much. And they're not going to lie if they're not. So it's now correlated, right? It's not random, right? Well, if you're drinking, I don't know, 60 drinks a week and you tell me 0, what's the measurement error? Really large, right? So the larger the measurement error that I think might exist, the more concerned I need to be with it, right? When I had really large measurement error here, it went from 60,000 down to 9,000. Now, when that measurement error was relatively small, even though it wasn't completely random, it was still non-classical, it only took us down, I think, what, from like 60,000 to 59,500. It still caused a bias, but that bias wasn't as large, okay? Now, we won't go into it in this class, but the next step would be, given what that relationship looks like between the measurement error and our X-ray, we could actually kind of determine what the size of that bias is, the exact value. We won't go that far in this class, but that would be kind of the next step, okay? For us, we just want to know what is causing us some bias here. So we didn't quite get to that last class. So here we're kind of thinking about what's another type of measurement error. Well, it could be based off that discussion we had about selection, right? That could kind of cause a similar issue. Basically, just error in that Y value is going to be correlated with X. So something we didn't talk about, and I'll kind of write this out, but I've got a slide for it. And we won't really, we won't go too deep into this, other than just knowing it exists. But I think it's worthwhile to show why it exists. And then when we get to instrumental variables, we actually have a way we can solve this, right? So let's say I had something that looked like this. Oops, forgot X here. And then X is a function of, just keep consistent with what I have in the slides, I think I used U. Right? So this is just another way to kind of identify an error term. So if Y depends on X, but X also depends on Y, we would kind of call this simultaneous causality. Okay. So maybe this is something like, you know, if I'm using my time to study, right, I'm not using my time to do other things. So maybe if I'm trying to predict how many hours of golf I play based off of how many hours I'm studying, well, if I study more hours, I inherently don't have as many hours to spend on golf, but then the more time I put into golf, the less time I have to spend kind of studying, right? There's this kind of like, I can see that relationship go in either direction. So we kind of have this reverse causality. If I try to run this regression, we'll notice if X, so Y depends on X, but X also depends on Y. Well, now when I run this regression, so if I just kind of rewrite this here, I've got, if I can write here today. I'd have something like this. Well, notice the issue here now is that once I've plugged in this equation, right, for X, I'm trying to predict Y using Y. I mean, that's going to be, you know, I can't do that, right? I know there's going to be a direct relationship if I try to predict Y. So we can't actually run this regression and get any meaningful estimates, right? I know Y is always going to impact Y, right? If Y goes up by 1, Y has to go up by 1, right? So if we have this reverse causality problem, we're going to have kind of an issue running these regressions. So we have a way around this, just called instrumental variables. So for us right now, we just know that this exists, right? We might have two variables. Oops, sorry. Where we have this simultaneous causality. We'll talk about later on how this data issue, we can solve it using something called instrumental variables. So that kind of rounds out kind of our discussion with kind of measurement error. The next thing that we're going to talk about is working with data sets, and we've kind of looked at these a little bit. I've simplified them and really not addressed the fact that we have with them. But we're going to look at data sets which we call panel data. So panel data sets. So go to our kind of this week's slides. Are going to be, and I'll kind of use this example because we have a data set we'll first start looking at. I had a bunch of students' test scores. So this is like in elementary school. So this is like I-STEP. You guys from Indiana, you probably had to take this when you were in, I don't know, elementary. I forget the exact grades you take it. But it's a standardized test score. I had students' test scores for the years 2006, 2009. So I had like the same student multiple times, multiple observations, but each observation was a different year. So I have one subject, but I've collected data on them at multiple points in time. It's just kind of panel data. I think when we first started talking about data sets, even before regression, I introduced this idea. We had cross-sectional panel data, time series. So this is our panel data set. So we're going to have a couple different types of panel data. So in my example, if I had every single student in Indiana, you might think it's what we call balanced. I've got every student, and I've gotten when they took this test for every 3 years. The problem is, what do some students' families do? Move, right? So I might not have every student for 3 years, maybe some I only have for 1 or 2. That would be what we call an unbalanced panel. For some subjects, I might have 3 observations. For others, I have 2. Well, if I'm running regressions, then that means there'll be some students who have 3 out of, and let's just have a number, 3 out of the 100 observations. They're going to carry more weight in my regression than the student who only shows up once. They would be 1 out of the 100 observations. So this is a problem because I'm now overweighting certain students compared to others. That would be the idea of an unbalanced panel data set. So we would prefer to have a balanced data set, but in some situations, that's not going to be the case, where we can't force students to stay in Indiana for 3 years just to make sure we have a balanced data set. So we're going to see how you could check this in Stata here in a second. But we'll first start talking about, okay, we have this panel data set. There's actually a really, I shouldn't use words like this. There's a really cool tool that we have to get rid of some issues that we talked about before, which is our omitted variable bias. Okay, so if I were to write out every student's kind of test score, so why I'm trying to predict their test score, and maybe I have a bunch of different factors on them. So like what their family's income was that year, that can change year to year. Maybe I have what their age was, that changes year to year. Maybe I have, I don't know, whether or not they had access to a private tutor, that could vary year to year. What the size of their classroom was every single year. All these different things that could change across time. So that's all going to be these variables x. So we usually didn't write these subscripts. Usually we're just thinking about like xi. So what was students' I test score and what was their income that year. Well, now because income of the family can change every single year, now we're looking at these test scores. They could be from 2006, 2007, 2008, and that student's family's income could change in those 3 years. So we have some variables, some control variables here that vary across time. Now, there's going to be some variables, though, that don't, right? So, for example, I used to use this one. Well, let's think of one that's not going to. So let's say I've got a student, and I want to include controls for what their race was, right? What race they are identified as. Was that going to change year to year? No, right? So there's going to be some variables that don't change. So even if I don't have access to that data, there will be certain characteristics that don't change year to year about these individuals. Some of them will. That's going to be kind of these controls X that we're writing here, but some of them won't, right? So these things that don't vary across time, I'm just going to kind of denote them as ZI because they don't depend on that time period. So I'm not using that subscript T because they're consistent across all 3 years that I have that student's observations for these test scores. Okay. Now, if I don't observe X, it's an omitted variable. That's going to be an issue, right? Because these omitted variables, if I'm omitting that variable of what the race was, and that's in any way correlated with family income, maybe it's going to be correlated with the number of hours they had with a private tutor, whatever these other X variables I'm interested in. Well, now my omitted variable is correlated with the variables I'm including. I have a bias, right? I have that omitted variable bias. So how can I solve this issue? Even if I don't have data on these things that don't vary across time, we can actually run what we call, let me see if I can get rid of this here. So there we go. We're going to use what we call first difference regression. Okay? So I've got this written out. But basically, if I were to do this year by year, let's say I only use the data coming from 2021. I run that regression. I don't know what these variables Z, I don't have information on them, but I know that they exist. I know that they should be helping me predict that student's test score Y. But when I run that regression for another time period, 2022, well, they're still going to be the same, right? They still should kind of give me information what that student's test score is. But my other kind of control variables, income, maybe class size, those things might be different in 2022 than they were in 2021. So if we take a first difference regression, so let's say I have all this data. I've got students' test scores in 2021 and 2022. I'm going to create a new data set where I look at the change in that student's test score. So I now have, I take their test score in 2022, I subtract it from 2021. Well, essentially, I'm taking this equation and I'm subtracting it from, I'm taking this equation and I'm subtracting this from 2022. So if I were just to kind of write out what that looks like, I now have this kind of regression equation. Now, technically this constant, maybe I could do kind of a better job of this. So if I'm trying to predict this student's test score in 2022, and I had here, maybe there was a constant from that year, and then I've got beta 1, 2022, beta 2, these variables that don't depend on time, and maybe this was the error term that existed in 2022. Just to kind of be complete here, we had the same thing going on in 2021, but maybe in 2021, that constant varied. Maybe there were some state level changes or something that caused that constant to be different in 2021 than it was in 2022. But those time invariant characteristics about the student, they haven't changed. And then maybe my error term, once again, because these time periods are different, maybe I have a slightly different error in 2021 than I did in 2022. When I subtract these two, kind of what would I be left with? And I simplify this a little bit in the slides, but really I'd have 2022 minus 2021 for that constant. I then would have beta 1 times the change in whatever those x variables were that I was controlling for that varied across time. But now notice I've got beta 2 zi minus beta 2 zi, these time invariant factors. And then I had my error term in 2022 minus that error term in 2021. Well, if these errors are completely random, I could really just think of this as like a new error term that would still be random and not correlated with my x values. What I've got here, though, notice all these time invariant factors, if I take this first difference approach, these go away. So even though I don't have data on what the student's race was, I don't have data on the neighborhood maybe they lived in, I don't have data on the level of funding their school, all of those factors I've essentially gotten rid of, right? But it's weird because I was controlling for them. It's just by taking this first difference, I was getting rid of them in both situations. And so it's almost like I'm controlling for these time invariant factors without actually having the data. So this first different approach really solves our kind of omitted variable bias issue, but only for things that are time invariant, right? That's why we were kind of writing the ZI. They were the same across every time period. Okay. So maybe it's like if I had a bunch of college level students, but it's coming from a bunch of different universities, even if I don't know what university those students went to, when I take this first difference approach, it would kind of control for what university they went to without even having the data. Okay. So this is kind of useful for us in terms of dealing with the data sets that we have. So we'll kind of use this first difference approach, and we'll look and see how do we do this in Stata and what does that do to our estimates. Okay. So go to this panel data set now, and let me make sure here. Make sure my global path is set. I change it here. Perfect. Right. So I've got this global. I'm going to kind of open this file that I put up on Canvas called first diff. So we'll take a look at this data. And I had this one set up a little bit nicer. I'll show you what happens if we don't here in a second. But basically, I've got, I can get this to expand. I've got, okay, grade size. And I've got total scores. So this was just a test score from 2 different time periods. So what I'm going to do is I'm going to try to predict the students' grades. based off their class size. I might think that being in larger classes, students get lost, and so they don't do as well. Anecdotally, in my sections of 300 for B251, the averages tend to be lower than like class sizes of 20 to 30, right? So I'm going to try to do this. Well, I have these variables. What I'm going to do is I'm going to create a new variable, which is, well, I want to predict total scores. I'm going to do the first difference. I'm going to take year 2027's test scores for that student, subtract the year the test scores they had from the year prior, 2006. I'm then going to do the same thing for grade size. I'm going to calculate that first difference. What their grade size was in 2007 minus what their grade size was in 2006. So if I were to do this, right, and then run that regression of those two variables, right, this is my first difference estimate. What I've done by doing this, I've essentially controlled for any factor that didn't change for that student across those two time periods without even having the data, right? This was a pretty joke of a data set. I didn't have like any controls. But by doing this first difference, I can control for a bunch of those other factors that I didn't have data on. In fact, if I were to not do that, so let's say I just ran this regression, where I didn't look at that first difference approach, and I try to just use 1 year data. This is going to contain a lot of omitted variable bias because I don't have any controls on anything on that student, right, other than their class size. The first difference approach should have omitted, right, should have controlled for all of those omitted, variables I didn't have. So if I look at this estimate, whoa, quite a bit different. It's a pretty large data set, 630,000 observations. But notice I get a coefficient that is not only of a different sign, right, but like it's almost twice the size in the opposite direction. So if I don't use this first difference approach, this contained a lot of omitted variable bias. My first difference approach removes any of that omitted variable bias that was being caused by student time invariant factors. Now, I still might have omitted variable bias from things that vary across time, but at least here I've eliminated some of that omitted variable bias. Eliminating some is better than eliminating none. So this is kind of our first difference approach, right? I can take data from time period 1, subtract it from time period 2, and I've now accounted for anything that was time invariant within those subjects. In my example here, within those students, okay? Any questions on that idea before we keep moving? Okay. So the second data set I had here was this player shot data. Nope. Why didn't it like that? Let's see here. Oh, did I change the name of it? Player shot data. Player shot, oh, I have a typo. Forgot my $sign. So if you're using the file that was posted, I forgot the $sign here, so we'll have to add that. So I've got this player shot data. I've got a couple different variables. Now here it's set up a little bit differently. So here, this is typically how we would look at a panel data set. It won't be like my previous one where I have different variables for every single year. It's going to be, here's that player's height in inches. So I don't know, Ahmad Coleman, I've got their data for 3 years. Here was their height in all 3 of those years. I've got what their free throw mean was in every single one of those years, right? So notice some of these things don't vary across time. Some of them do. So I've got some things that are varying with time, some things that aren't. I've got the average attendance, I think, of those players, wherever team they played for, what the average attendance was for their games. I've got whether or not they were in Division I. I don't know. I forget why this isn't. Oh, this was if all of their games were played against Division I schools, what proportion were not played, were played against some. So I've got, just a bunch of different data here. So what I can do is first, before we even get to kind of thinking about that first difference approach, I want to check to see, is this data set balanced or not? I can kind of notice here for some, if I just look at it, sometimes it's obvious. Okay, I've got this player for all 3 years. but this player I've only got for 2 years, right? So one way to kind of quickly check to see if you have a balanced panel data set is just generate a random, like a variable, kind of call it whatever you want. I call it count var. Set it equal to 1. So all this really does is give me this variable that's equal to 1 for every observation. Now, why is that going to be useful? So we can now start to use this command called by sort. So you can type it out, by sort, or the shorthand you can use in Stata is just bys. Right? So what that does is it sorts the data by whatever you put here. So I'm going to sort this data by player ID. So there, it's going to put every single player, like group their observations together. And then within each one of those players, we're now going to use this egen command. And that's going to say, for all the observations of this player, add up or sum up this count variable and give me the sum of that count variable. I'm going to call it total seasons. So if there was a player in this data set for 3 years, it would look at that player, take count variable plus count variable plus count variable, and return to me they were in this data set for 3 total seasons. If they were only in the data set for 2 years, count variable plus count variable, it would give me they're in the total seasons. Sorry, the total seasons I have for them is only 2. So once we have this kind of panel data set, I can use these by sort commands by group, creating these different variables. So notice, like these players were in the data set for 3. This person actually ends up, I guess I had 4. I didn't have 3 years. Some of them have 4 years of data. I didn't even look at this correctly, right? We've got some for 3, some for 4, some 2, etc. Now, if I don't want to look at the data individually, I could always use kind of that tab command. And it kind of shows me, okay, I've got 4,000 players for all 4 time periods. I've got 8,000 players only for 3. I've got I've got 15,000 of these players for only 2 time periods, 15,000 for 1. Why is this likely going to be the case? If I grabbed 4 years of data, I believe this was college basketball. And so players are going to be graduating or entering. Right? So this is a very unbalanced panel data set, right? There's going to be some players who carry the weight 4 out of the total number of observations. And there's going to be some players who only have 1 out of however many total number of observations I have. So the information from some players is going to carry more weight in my regression results. We don't generally like this. Right? So what's a way around this? Well, it's not great, right? But if I wanted to make sure I'm only comparing players that have the same number of years in this data set, I could run my regression, but include an if statement and only run it for the players I have all 4 years of data on, right? Now that gets rid of a bunch of data. That's unfortunate, right? I don't like to do that, but if I want a truly balanced panel data set, given the limitations of my data, that's what I would have to do here, okay? Now there's other things we can do outside of this class to kind of address this and adjust for this kind of unbalanced panel data, but for the sake of what we're going to do in this class, that would be kind of our solution up to this point, based off what we've talked about. So I can kind of use this to kind of quickly check to see if I have, I scroll down, if I have kind of a balanced panel data set. Now, one command, and I think I introduced this later in the do file, but just to kind of get at it here, we won't do a whole lot with it. But I can set up a data set if I identify by looking at it that I have a panel data set. So here I said, okay, I've got the same player in multiple time periods. I've got this player multiple time. Okay, I've got for each individual, I have multiple periods of time collected. That's a panel data set. So what I'm going to do is I'm going to tell Stata, hey, don't treat this as cross-sectional, right? This isn't every observation, isn't just one specific year player. Some of these players show up multiple time periods. I can use this xtset command. The first thing that I tell it, so if I was going to be kind of giving you some general instructions here. I'm going to first tell it what my subject is. So in this example, it was players by season. I think if I was looking at like macro level data, it might be country by year, right? And so I just tell it the subject. I tell it kind of what that time period variable is. it now kind of sets this up as a panel data set. Okay. If I do that, I can start to use built-in commands in Stata. So if I use this ddot command after I run this xt set, so I'm going to kind of tell Stata, treat this like a panel data set. Oh, well, one nice thing Stata does for me, instead of checking this with the code we had earlier, notice it tells me it's unbalanced, right? That some players I have all 4 time periods, but some I don't. Okay, so this tells me whether or not my data set is balanced or not. Now, I don't know how unbalanced it is. This showed me it was very unbalanced, right? So this is probably an approach that gives me more information about how unbalanced my data set is. But at least here it kind of tells me there's at least some observations, there's at least some players, some subjects I don't have all 4 years of data on. Okay. So once I've set it up this way, let's say I was trying to predict the free throw mean of players based off of the current attendance, right? The attendance that they faced in that year. So, maybe the idea is if I'm playing in front of more people, I don't know, I get nervous, I don't do as well, right? Something like that. And so if I were to just run this regression like we typically would, maybe I get this estimate of 0.0009, right? So when attendance goes up by, I don't know if this was one person, I'm guessing it was something like hundreds or something like that, but whatever the unit is, if attendance goes up, it looks like it's actually positively impacting that player performance. Now, the problem is players who are usually playing in front of more people are likely going to be in Division I schools, right? They might be on better teams, right? They might be of higher quality because people want to go watch better performing teams. They're more likely to have higher attendance. And so there's likely a lot of omitted variable bias that I have built in here. So what I can do, if I've got this up as a panel data set, essentially, instead of like doing this by hand like we did up here, this ddot command will go through the data, it sorts it by player season, and then calculates what was the change or what was the difference in their free throw mean from this year compared to last year. And then it also looks at that X variable and says, what was the change in the average attendance that that player played in front of from this year to last year? It's doing the first difference for us, okay? And we can do this now. In my earlier example, I could only do that with 2 years of data. It can calculate this difference, taking the difference between 2022 and 21, 2021 and 2020, 2020 and 2019, and then use all of that data in the same regression, where because it's looking at those first differences, every single time it calculates those, it gets rid of all these time invariant factors, those ZIs that we were looking at earlier, okay? So if I run this regression, once again, when you eliminate that omitted variable bias, we might find a coefficient estimate that is the complete opposite sign. So, it's about the same size, maybe a little bit smaller, but it's now negative instead of positive. So now the thought here is controlling for all these things that don't change, like the player is still, same overall, kind of has the same overall height. Maybe I didn't have that, might have it in my data, but I'm not controlling for it. Maybe that they're the same weight, they're the same race, they have the same number of years of experience in high school, they've got all these other things that would be consistent across time. I'm now controlling for all those factors without even having data on them. Makes it a lot easier on us as like, I don't know, I wouldn't necessarily, it sounds very pretentious, but as data scientists, right? Or as people who are using data to try to ask, oh my gosh, try to answer these questions, okay? Now also notice what can change for my statistical significance. Well, my p-value changed here quite a bit as well. So here it's not quite statistically significant, whereas before it was highly statistically significant. And that's because we're eliminating some of this omitted variable bias. That can change not only the size of our estimate, but also that statistical significance. Okay? So this is probably a better way to kind of run these first difference regressions, because we don't only have to have 2 time periods now, we can have as many time periods as we want. And you can imagine with something like country level data, I might have 50 years of data that I'd want to run these regressions for. Okay. Is that any questions on this idea before we keep moving? Okay. So this first difference approach is good. It's a good first kind of look at things. But we can actually take this one step further. Okay? So instead of looking at this first difference regression, let's say I wrote out that regression where I was thinking about these time invariant factors and I haven't taken the first difference yet. Well, if I don't have data on Z, I know that when I run this regression without it, I'll have omitted variable bias. Well, I could kind of rewrite this, whereas even though I have a constant, I can think about all of these omitted variables Z. All that's really doing is saying that for this individual, their starting predicted value for Y is going to be different. So essentially, each individual has their own constant when we're trying to predict these Y values. What does that kind of sound similar to? So for every single, let's say I was estimating this and I thought every country might have a different starting point for their line of best fit, what we're actually including there. But its most simple form. Remember when I said I wanted to predict like wages based off the number of years of experience? I thought that that might be different for males versus females. Even if that slope of that line of best fit is the same, when I include a dummy variable for if they're male or female, that shifted that line of best fit. It essentially created a different constant or a different starting point for those two groups. Well, I no longer only have males and females, I have every single player that could have a different starting point. But if I could include a dummy variable for whether or not this was player Joe Smith, whether or not the observation was from player, I don't know, choose another random name, right? Right, keep going through. I would include a dummy variable for every single player, but leave out one of them. So what we would call that is fixed effects. And we can do that very easily in Stata. Now, what that'll do is that constant for that player is something that is time invariant. It's essentially, by including a dummy variable for that player, I've captured the effect of every time invariant factor that matters for this Y variable. So if I was writing that out, it's almost like I've got kind of a new kind of constant for each individual, and that have like all these different dummy variables. So notice here I wrote, let's say I had 50 players. Initially, you might think, well, I would include like 50 different dummy variables for was it player Joe Smith? Was it player Zach Evans? Was it player blah, 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 blah? Why don't I include all 50 there? Because if I knew the first 49 were all equal to 0, I know that player must be the 50th name. So if I included all 50, what issue would I have? Perfect multilinear. Right? So I've got to leave one group out, right? And I say group here, one individual, right? So that's why we would kind of have like, if I had 50 players, I'd have 49 different dummy variables. Well, this is going to be a pain to do, right? If I had to do this by hand, but we've actually kind of already seen how we can do this in Stata. Oops. So we'll take a look at a couple different approaches. There's a couple different ways we could code this. So I'll open up first this panel data set, which is birth data by state. Why doesn't it like this? I was copying, pasting, and I must have forgot to copy the $sign in every single one of these lines. So I apologize for that. So I'll update this do file after class. So I put all those $signs in there if you're kind of using that global path command. So I open up this data set. I take a look here. All right, so I've got the number of births, the average age of the mother in that state, and the average birth weight. And I've got what? Looks like here about 6 different years of data. And this is for every single state. So this is no longer individual level data. It's like state level. So the subject is my state and the time is year, right? So do I not have the birth data up there? Let me see. This would be, I might have forgot to, let's see if I put it here and just forgot to select it. If not, I can upload it here real quick. Oh, I must have, I was dragging these over. Forgot to include it. So let's go files here. Sorry, thank you for asking me that. Now let me just keep going. There we go. Now, if you want to open it up, you can kind of work along with me, and I'll add it to the home page here real quick. There we go. Add on. Okay, so we're going to use this birth data by state. So I open that up, we kind of take a look at it, and this is kind of what our data set looked like. So I go back to my do file. Now, I could kind of use this method I showed you earlier, which is just create this variable, the count variable equal to 1 for every observation. Then by sort state, so by each state, calculate the total number of years by simply adding up the number of kind of years I have them in the data set, or add up count variable for every single state observation. I use tab to kind of look at, okay, what's that distribution look like? Here I've got a nice balanced panel data set. Every state I have in here for 6 years. In fact, I must have Washington, D.C. or Puerto Rico. I don't know which one it is, right? Because I actually have 51. So I'm then going to kind of say, okay, if I run this regression where I'm trying to predict the average birth weight in a state based off of the average age of the mother, right? So typically we think of like older mothers tend to have less healthy pregnancies, less healthy. So birth weight would like to be lower if we're using birth weight as a measure of health. It's not perfect, but that's something that you see in health econ where that's kind of a good proxy for health of the child. So I run this regression, I get a coefficient of about 14.8. So for every additional year, the average age of the mother goes up in a state, birth weight actually goes up. Oh, okay, this goes against what I just said. And the problem is, I don't have any other controls. There's likely a lot of omitted variable bias here, okay? So I might think about, okay, what are some factors that might be correlated with age that are also correlated with birth weight, right? Well, you know, if I compare like Utah to New York, right? I mean, there's huge differences in the religious composition of those two states. There's also a very big difference in the overall level of income or population or just the life. I'm not controlling for a lot of important factors here. So one way I could do this is something that we've actually already done before, which is I can use kind of this i.state command, right? We said that takes a categorical variable and it puts in a dummy variable for every possible value. So if I put i.state, what it should do is put in a dummy variable for every single state and leave one of them out. Now, the problem with that is it's going to give me an error. Why? Okay, I forgot. I can't use that command if it's a string, right? So we said, if we remember, what's one way I have around that? I can use this encode command. So even though a lot of the time the data is downloaded as characters, like an actual word shows up as red in the data, we said I can encode that and essentially just assign every state a number. So every time I see this word Alabama, I assign it a 1. Every time I see Arkansas, it would assign it a 2. So when I use that encode command, it looks like I have the exact same variable, but notice it went to blue. And when we clicked on it, oh yeah, every state name is actually technically behind the scenes being identified by a number. Now I can use that i.dot command because it's numerical. It seems like semantics here. It's just the way on the back end state is able to read strings versus numerical values. So I now have that encoded. I created this new variable, and I often do this like when I'm doing this on my own if I were to. Instead of, I don't want to just like get rid of the old variable. I still want to keep the string just in case I want to go back and look at that state for whatever reason. Just be able to compare. I'm going to generate a new variable, right? I'm just going to call it state FE. It's the one I can use to calculate or create these fixed effects. So now when I do that, whoa, my regression, I'm still predicting the birth weight from mother's average age of the mother, but I've now got every single state has a dummy variable. Now, which one did I leave out? I actually have no idea, right? So this is kind of a problem, but we can kind of solve this here in a second, okay? So that's one way we could do this, right? Now, the other way of doing this is we have this areg command. And for the sake of what we're doing in this class, there are some differences in what Stata is doing on the back end when we use these different commands. for the sake of what we're doing, all of them will essentially produce the same results, all right? So it's a little bit more complicated once you would start to add in additional controls and once we start to think about some more complicated issues. But for where we're going to be at, all of these are just 3 different ways of doing the same thing. So I could use that IDOT command. I could use this, what we call, it's areg. It's basically absorbing. So you'll see some differences here in what it's doing. But it's very similar, just like, the syntax is a little bit different. Instead of IDOT, I have to put comma and then what variable I want to absorb, what I want to kind of create the fixed effects for. The reason why we sometimes like this is because now we don't have to look at every single state's individual coefficient. It's still controlling for all those. It's still throwing those kind of dummy variables in there. It's just not displaying them to me, right? So notice when I do this, I get the exact same coefficient estimate. And when we compare that to not using fixed effects, we were going from a coefficient of 14.8 and highly statistically significant to now we've got what? An estimate of -33 and high. So it's, once again, almost double in size and of a different sign. This goes to show the importance of fixed effects is going to eliminate a lot of omitted variable bias. Okay. And then we have a third and final way of doing this. So if I set this up as a panel data set, so once again, I'll kind of show you an issue that can exist. Maybe originally I think, okay, I'm going to set this up as a panel data set. My subjects now are not students, right? They're states. And my time variable is year. But if I try to use that original state variable, it's going to give me an error because once again, I can't use a string variable, right? I had to use that encode command to create this new variable of state FE, which even though it looked like it was text, the blue reminds me, oh yeah, there's a number behind the scenes here, okay? So if I kind of set this up as a panel data set, I then use this xtreg command. So once again, we're running a regression, but this is telling it, use the panel data that I just set up, okay? And then I want to use those same 2 variables in my regression, but comma FE, that includes these fixed effects. So it essentially will create all those dummy variables for you. And hopefully, if I told you these are 3 different ways of doing the same thing, sure enough, we get the exact same coefficient estimate. So just 3 different ways of including all these dummy variables, 1 for every single state here. Okay. Excuse me. Now, one thing that also comes out in this output that's kind of nice, when I set it up as a panel data, it told me it was balanced. But notice here, it tells me the number of observations. It tells me I have 51 groups. And it's telling me that the minimum, the maximum for each group is 6, which essentially means every single state I have 6 years of data. So this would kind of also tell me I've got a balanced panel data set. Okay. Now there's some additional statistics that we won't use in this class, but if we were kind of continuing to the next, so I'm still getting used to all the numbers of courses. This is only my 3rd year here, but was it 401? Is that the next, I forget the name of it, but it's basically the next level of econometrics kind of past this, right? You would start to dive into maybe what some more of these statistics are telling you that you're getting. For us, we're just worried about the coefficient estimate using fixed effects for now, okay? So really just 3 different ways of doing the same thing. I'll probably save this 4th way for next class, but there's actually a 4th type of regression we can use to also kind of essentially use fixed effects, okay? Let me think if there's anything else I want to say here. We'll save this for next class. And then just to make sure we leave on a good place here. So this is, yep, we'll save this. And then we'll do autocorrelate. Okay, perfect. We are exactly where I want to be for next class. So what we're going to do is kind of look at this in-class quiz. Well, I'll leave it too. We'll get done early, but kind of get, so I'm going to publish this. We'll kind of take a look at this here. This should show up on the main homepage. You could go to the quizzes tab as well. Ooh. But under panel data, we're going to take a look at this in class quiz number 10. Going to go here so we can preview this together. Don't know if I've got a code on this or remember what it is. So 37.99 would be the code for the day. We're then going to take a look at this here. I think I only had kind of 2 questions in here. So this is where we haven't quite touched on these topics, but based off what we know about previous topics, I think we should be able to answer these relatively easily. Okay. So if I run a model without fixed effects, what's going to happen if I use the fixed effects model to my R squared? Okay. So not my adjusted R squared, but my R squared. When I say we use fixed effects, it's essentially like we're creating a dummy variable for every single person, every single state, whatever our subject is. So like in my state example, if I'm including 50 dummy variables, I'm adding 50 variables, what's going to happen to my R squared for sure? I'm adding more variables, it has to go up, right? So these fixed effects regressions, it kind of makes sense. If I'm able to account for all these omitted variables, I should be able to come up with better predictions for Y, right? So I should be increasing the proportion of variation I can explain in that Y variable. And then all the way back to what we talked about earlier, simply adding variables into our regression will always increase our R squared. Now, our adjusted R squared, we said if we just start throwing in variables, maybe I can increase that R squared, but what does the adjusted R squared do? Penalizes me. So in fact, if I don't have really good controls, imagine I had my like player shot example. I'm not going to have 50 dummy variables. I'm going to have thousands. So even though it increases my R squared, when we think about that adjusted R squared, that scaling factor is what? N minus 1 over N minus K minus 1. K is now going to be like thousands, right? So my adjusted R squared from fixed effects, that effect is going to be that it pulls that adjusted R squared down by a lot, right? So when we're thinking about that adjusted R squared, I don't really know. Because I know my R squared is going to go up, but I know that scaling factor could go up quite a bit. So there we don't know what's going to happen to our adjusted R squared when we use fixed effects. Okay? Does that make, once again, we're kind of reusing things we already talked about because all fixed effects is doing is adding in a bunch of additional variables. They're all dummy variables, but you know, we're still adding them into our regression. Okay? Any questions on that idea? Okay with this problem? Just clear what the answers are here. So everyone's going to get this correct when I look at the submissions. Okay. So let's say instead, I'm thinking about, I want to predict the student's GPA based off the number of credit hours they take. So this is like maybe all of you. I'm interested, I got data on you. If I use a first difference approach instead of fixed effects, which of the following is not going to be true? Okay. So this is a little bit tricky, and we didn't quite touch on this, but we can talk through the other things and think about what should be true. So I said a first difference approach, it's essentially controlling for all these time invariant factors. So if I used first difference approach or fixed effects, I should get estimates that are of the exact same size. Right? Now, if I'm getting estimates of the same size, if it's 2 different ways of doing the same thing, I should also get that they have the same statistical significance. So if we go back and look at all those regressions, right, our test statistic was always, well, I went too far here because it's a different data set, right? They're all going to be exactly that same, that not negative 9.44. Okay. Now, what won't be true, so my p-value, my test statistic should all kind of be the same. But when we're using that first difference approach, remember when I wrote this out, what regression am I actually running? So with our fixed effects, I was just taking Y from time period T. I had X from time period T, and then I had a bunch of different dummy variables. So notice my Y variable from the first difference regression is not the same, right? Because what did I do to my y variable here? I actually created the change in y. So really the interpretation from our fixed effect, the interpretation from our first difference model was how does the change in x, what change does it, say this, slowed myself down. So what is the impact of a change in x on the predicted change in y? That's very different than just saying a 1 unit increase in x. What impact would that have on the unit change in y? So even though our first difference approach and our fixed effects both help control for those time invariant factors, they will eliminate the same omitted variable bias. The interpretation of our coefficient is very different, right? That first different approach puts it into changes in x, causes a change in the predicted change in y, right? Whereas here, this is going to be more like what we want, right? So this is a 1 unit increase in x causes our predicted y value to change by whatever beta 1. That's more like we're thinking about like the average age of the mother. If the average age of the mother goes up by 1, what's the expected increase or decrease in the average birth weight? We don't want to think about, well, what if there's a 1 unit change in the mother's years? What would kind of impact would that have on the change in the average birth weight? Because now we start to think about, well, there might be some real nonlinearities, right? Or if it wasn't like age where you always see kind of 1 year higher, maybe this is something like, I don't know, income going up by kind of $1, or if we had something that was measured in percentages, the units might not match up. And so we're going to have a slightly different interpretation, okay? Because this is the change in that variable, like from 1 year to the next. This is the actual underlying value of that x variable in time period t, whatever year that is. Okay? So when we're looking at first differences and fixed effects kind of regressions, they'll give us kind of estimates that are of the same size. Standard errors will be the same, p-values, but the interpretation is going to be slightly different, right? Because we don't really have the same y value. Our y value for that first difference is now the change in that y value. So the only one that should, not be true here is the interpretation won't be exactly the same. So they're both solutions to that omitted variable bias problem. We have a panel data set, slightly different. So we usually don't see, unless you have 2 time periods, most people don't use this first difference approach. Usually you'll see people use these fixed effects models. Any questions? Is that clear what that answer is? That second question. It's just the interpretation that's going to be a little bit different. So saying the interpretation is the same, that one won't be true. Okay. Any other broad questions here? So make sure you're getting this submitted here before 2 o'clock. One a little bit early before I get you guys out of here. So just as a reminder, I'm going to change the due date on that problem set. We come down here. So I had that quiz 5 set to be at the end of the day Thursday. So we got a little bit more time to kind of think about that. Once again, we kind of touched on measurement error here again today, but really anything you need for that quiz, we worked through already last week. And then that problem set, I'm going to change the due date to the end of the day tomorrow. Okay. So if you have last minute questions, my usual kind of scheduled office hours in the morning tomorrow, feel free to stop by and clarification. Other than that, my earlier section, somebody asked me if I was going to a tea time after class today. I said, no, it's just nice out. I'm trying to dress with the weather. So make sure if you have any questions, feel free to stop by tomorrow. Otherwise, enjoy the weather, and I will see you guys on Thursday.